It feels like it's been forever since we did this live in class. I've done a lot of pre-recordings at the house for you. But let's actually do one together.
Yay.
I just want to review what you should have in your notebooks already. There's a couple items where I'll be like, you don't have to have it. You have it only if you really feel that you need it, okay? Definitely everyone must have the circle vocabulary. It was for grade, so if you still haven't finished copying these notes, you has a 0 until you show me that you've copied all these notes, okay? So please make sure that you get that cleared out as soon as possible. It was 4 pages worth, okay? Yeah. Then, I cut for chapter 10, lesson 1, I cut a radius and diameter. You do not have to have these notes if you're feeling comfortable with radius and diameter. You're welcome to have them if you feel that they will help you. All right, additionally, with circumference, the same way. I clearly cut off the title on that page. Dirt. Sum of central angles was the next one, and this one was covering 10-2. Again, one of those optional ones. If you can think through sum of central angles without any assistance, you don't have to have these notes. But if you feel you need them, they are available here in my notebook and on YouTube. Up next was angle measures, or excuse me, arc measures, which were different from arc length. Arc measure were the measures of degrees, just like in angles, and it was always measuring equal to the central angle. Okay, so we had all these 3 different type of arcs and their measures. Again, if you don't feel that you need these, you can skip these notes, but if you feel they're important to you, please get them down. After that, we had the information on arc length. This formula came straight from your notes on the definition of arc length. It had the formula. And this is more of an example of how you run through the algebra of calculating the arc length from the formula. Up next, I did a quick video for 10-4, which was the inscribed angle measure. And it talked about the formula that you would use in order to calculate the inscribed angle. Here it is. When we have the angle with the vertex on the circle, and then the sides of the angle forming some secants, and a quick example of how you would calculate those. 10-4 dealt with this a lot. So if we're needing help with 10-4 and you haven't gotten these notes or this video, please do so. We'll go ahead and continue with today's item. So go ahead and make sure that you've gotten the objectives down and the title. I'm going to catch up to you here because I know most of you have already done it. So we're looking at secants, tangents, and angle measures today, and in some cases arc measure as well. Today is the 4th of April. Happy birthday to mother-in-law.
Oh, happy birthday.
Here's some golf claps going on in the background. Like, all right. Huge applause, rock it out. Everyone comes over and goes, what's going on? And we're like, we're just saying happy birthday, that's all. All right. We have 4 bullet points. Let's talk about the first one. The first one deals with the measures of inscribed arcs. Also, it deals with angles, but it's not the inscribed angle. This isn't the angle that the vertex is on the circle. The vertex of these angles are somewhere inside or outside of the circle, and you can get arc measures to relate to it. So we're going to talk about measures of inscribed arcs. These inscribed arcs, as I mentioned, are going to be created by 2 secants, and they intersect in different ways. We've got 2 different cases, so if you'll set up that title and then cut your note-taking space into about 2 sections, roughly equal to each other. The first case is what happens when these secants intersect outside of the circle. So this is an exterior intersection. Let's draw that picture. And I'm going to zoom in real tight on here. maybe zoom so I can focus. Focus! Okay. So here's my circle. Again, you can freehand it. It doesn't have to be perfect. And we want to draw two secants. Secants are lines that intersect the circle in two places. So one secant line and two secant line. But the important part is that the intersection happens outside of the circle. Okay? When it happens outside the circle, you have three things that happen. Three things that get created. Right here, you create an angle measure, which we'll call theta. Right here, you create a small arc, sometimes referred to as a minor arc, but it's not the minor arc from the vocabulary, so I want to give it to you in a different way. So we'll just call it the smaller of the two arcs. And then you have the larger of the two arcs. So those three things get created. From these three things, we get this formula. The measure of that angle theta is given by the measure of the large arc. I'm going to abbreviate, capital letters LRG for large, minus lowercase mSLL for small. So the measure of the large arc minus the measure of the small arc, divide that result by 2, and you will get the measurement of the angle that is creating both of those arcs as those secants cut through the circle. Okay? Fairly simple? Seems okay? All right. Let's look at the other case. The case in which...
So once we get, like, we get the, when, like, we subtract them and we divide by 2 and we get the...
Yep. The second case is what happens when these secants intersect inside of the circle. So your diagram is going to again have a circle and again have two secants, but this time the intersection happens somewhere inside the circle. Note that it doesn't have to happen in the center of the circle, although it could, but strictly speaking, it doesn't have to. So you're looking at that intersection point happening right inside the circle somewhere. Again, you're going to create this angle right here, which we will denote by theta. And it's going to be congruent to this other angle here that gets created. That's also theta.
It's a smaller one, right? So smaller.
You've got different size arcs going on, but we're talking about this angle measure in here. This angle measure is also theta, because they're vertical angles. You remember from way back toward the beginning of the year, we talked about vertical angles and that they're congruent to each other. So same thing happens here. And once again, you create two arcs. One might be smaller than the other, but it's always hard to tell which one is which. So we're going to call them not small and big arc, but arc 1 and arc 2. The formula for finding theta then in this setup looks like this. Theta equals the average of arc 1 and arc 2. So you're going to take those arc measures and add them together before you divide by 2. I made a what? An arc?
Yeah.
Where's my arc?
On top of the 2. Yeah.
Okay. Oh, right here?
Yeah.
Yeah, I didn't draw it straight. All right, let me know when you're done with this one.
Miss, can you move it over a little bit?
All right, we ready to move on to the next one? Yes? All right. All right, the next one is a theorem, and this theorem is dealing with tangents and helps you decide how tangents work. So this is the tangent theorem. This theorem says this: the tangent of a circle is perpendicular to, we're going to use the little symbol for perpendicular. Remember, it's the upside down capital letter T is the symbol for perpendicular. The tangent of a circle is perpendicular to the radius of the circle. And it's perpendicular at the point of tangency. A lot of vocabulary words going on here. What was the tangent? Flipping back, I can hear papers rustling.
A line in the same place as a curve that intersects the curve that can point.
The line in the same plane as some sort of curve or circle that intersects that curve or circle in exactly one point. That is a tangent. So let's go ahead and draw that setup real quick so that we can see it. We're going to use a circle. So there's our circle, and we need a line that's on the same plane, which basically means on the same sheet of paper. So draw the circle, please don't flip the page and then draw your line. Okay, draw the line here on the same sheet of paper. And then you want it to touch the circle in just one point. There it is, there's my tangent line. And then we need a radius, and it wants the intersection between the radius and the tangent to be at the point of tangency. So what did the point of tangency mean?
Exactly where it pitches the circle.
Exactly. It's the point where the tangent line and the circle meet up. So this point right here would be our point of tangency. This is our tangent line. And so this would be our radius. What this theorem tells us is that this line, the radius, and this line, the tangent line, intersect at a right angle. They are perpendicular to each other. Feeling okay with that one? All right, I'll give you a couple more seconds just to fill in your diagrams. Then we'll move on to the next one. Thumbs up when you're ready. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you.
I'm trying to look at your videos.
Okay. Thank you. All right. So the very last theorem that we have today, because remember I promised you there were only 4 new items for today, is called the equivalent tangent theorem. The name seems to imply that we're going to have some tangents and that they're going to be equal in measure to each other. Equivalent tangents. Here's what this theorem says in words, and then we'll draw a picture. It says, if 2 segments drawn to a circle from a common exterior point are tangents. So if 2 segments are tangents, and these tangents have to be drawn to the circle from some same point outside the circle, then the segments are congruent. I totally misspelled congruent. I think I put a W in there. Sorry. Don't hate me. All right, let's draw a real quick picture right here, and then we'll save the rest of the space for one brief example, and we should be done. So we're going to have two segments coming from the same point. So there's two segments coming from the same point. And they have to be drawn to a circle, so I need to put a circle in here somewhere. There it is. And I have to make sure that these lines are tangent, so they have to touch the circle at just one point each. When I have a setup that looks like this, then it means that this segment right here and this segment right here are congruent to each other. Please note that those segments go from the common point to a point of tangency. And so we're talking about this piece right here. Okay? Those pieces are the pieces that are congruent to each other. Let's work an example so we can get a better view of what this looks like. Okay, so I'm going to draw the same sort of setup. I'm just going to make it a little larger. This kind of almost ends up looking like an ice cream cone. Yum. Now I'm hungry.
Yes, I've been hungry.
You've been hungry? Okay, there they are. I need some letter names, 4 of them.
No,
R.
C, R, A,
EJ.
different.
D,
E.
L,
E.
J.
E.
J, I heard from a completely different voice back there because I heard a lot of these voices over here. There we go. So
Jar.
G-A-R-C. It's a jar and a car. The car is a jar. There it is. All right, let's make up some numbers here.
6.
6,
Whoa.
7, and
Two.
24.
Oh, I saw you.
All right. Alrighty, there we go. I have no idea how these numbers are going to work out. Okay, so cross your fingers that these are whole numbers and not some weird ugly fractions. I'm sorry if they are.
Pi.
All right. Do we have a circle?
Yes.
Do we have two segments?
No.
I don't know what segments are.
Segments are pieces of lines.
Yes.
Are they
Actually-
drawn to the circle from some common point outside
Yeah.
the circle?
Yeah.
Do those lines appear tangent?
Miss, those are rays.
Okay, I agree. They're technically rays, but we're going to call them segments. That means that according to this theorem, these two line segments are congruent, which means this measure and this measure are equal. And so I can write my equation as the measure of this segment equals the measure of this segment. And now I set the geometry aside, I pretend I'm in algebra, and I solve this equation for x.
7x minus 7x. Cancel it out.
Yep, sounds like we want to get rid of this 7x over here, so we're going to go ahead and do that in one step. So I have 2x minus 6 equals 24. Let's get rid of
Oh,
this
yeah.
6. And how do I get rid of a minus 6? Plus 6.
24 plus it's 30.
And then get rid of the 2.
Divide by 2.
Divide by 2, he says, because they're multiplying by 2.
X is 15.
X is 15. Ooh, I did good with these numbers today. Questions on what was introduced today?
No.
All right, so let's look into the assignments 10.5 and 10.6. To do a really brief walkthrough, we're just going to talk about what section of these notes are going to best help you in completing those items. All right, looking at 10.5, first off, the first section is asking you to determine whether the segment is tangent to the given circle.
Did you just get this today or?
They've been out there since Friday, yeah.
Really?
Yeah. If you didn't pick it up, go pick it up. They're still
No,
up
because
coming.
the only ones I saw were the circles.
The
They weren't
circles?
up there for me.
They should have been. Maybe I had just had them in a different spot for you.
No, like the desk was filled and that desk was filled too.
Huh. Weird. We'll just double check it again right after, yeah?
Hey.
All right. So looking at determining whether a line is tangent or not, which of our theorems talks about tangents?
The second theorem.
The second
Tangent
theorem?
Tangent theorem.
Tangent theorem. The equivalent tangent theorem requires that we already have tangents. So the tangent theorem is what tells us whether we have tangents or not. So read that theorem very quickly again.
The tangent of a circle is perpendicular to one.
The radius.
The radius of the circle at the point of tangency.
So a segment is a tangent if it's perpendicular to the radius of the circle at the point of tangency. So let's look at this diagram again, and I'm going to zoom in nice and tight here for you. All right. Where's the radius?
L.
28.
At L to M. There's a radius because it goes from the center L to a point on the circle M. And it says, determine whether each segment is a tangent. So this segment MP, we want to know if this segment is a tangent. If it's a tangent, we should expect to have some sort of right angle right here at M, correct?
Yes.
But I don't have a way to measure this angle.
Oh, yes.
But I can still decide whether it's a right angle or not. Notice how I formed some sort of triangle? If this were a right angle, what kind of triangle would this be? A right triangle, definitely. If it's a right triangle, what theorem, what formula does it have to make true? This would end up being 90, but what theorem can we use?
Pythagorean.
Yeah, Pythagorean theorem, that's the big right triangle theorem. That's the one that says this side A squared plus this side B squared is equal to this side C squared. So if we take this and square it, and if we take this and square it and add them together, I should get the same number as if I took this one and squared it.
Yeah, because it's a right triangle.
If it's equal, this thing's a right triangle. If this thing's a right triangle, then ML is perpendicular to MP, making this a right angle. And because our theorem says that, the tangent is perpendicular to the radius, MP is shown to be a tangent. Do you see all that justification?
I was supposed to write it on the...
Justify your answer. So show you working out the Pythagorean theorem, and then show through that argument. Write it out in English words the best that you can. Because the Pythagorean theorem showed that a squared plus b squared is equal to c squared, this angle here at M is a 90-degree angle. Since it's 90, this segment is perpendicular to this segment, and because of my tangent theorem, MP must be a tangent. Okay? So something along those lines is what you're going to try to write out. If the a squared plus b squared does not equal c squared, then there's no way this could have been a right angle, so there's no way that this could have been a tangent.
So if it's not equal, you just say it's not tangent?
It's not equal, it's not tangent, because it doesn't fulfill the Pythagorean theorem. It doesn't create the right angle that you need by the theorem, by the tangent theorem, in order to say it's a tangent. That's it. Okay, so there's 1 and 2 for you. Quick glance at 3 and 4. You're having to find the value of x, and it tells you that assume that the segments that look tangent are in fact tangent. So if it looks like it's a tangent, doesn't clearly cut it through twice, it's going to be a tangent for you. Round to the nearest tenth if you have to. Which theorem could you use to get through these?
The one that we just used right now, the equivalent tangent theorem?
Yep, one of the ones you just used, the equivalent tangent theorem for number 3. Number 4 might be slightly different. So make sure that, you're going back and you're thinking through, what do I know about tangents?
Yes. So we can take that. So
Mhm.
equal so
Yes.
like that.
Exactly like that.
Can I talk about
All right, look at 5 and 6. Again, you're assuming that things that look to be tangent are in fact tangent. These figures look a little more complicated, yeah? But it's only because you got a lot of more stuff going on, but all the same processes remain the same. I have a circle. Yes? And at some spots, it looks like I've got 2 segments coming off a common point. And these things appear tangent. So which of your formulas has
the measures of each system?
2 segments that are possibly tangents going toward a circle from a common point? Yeah, the equivalent tangent theorem that says that this segment is equal to this segment. They're congruent, their measures are equal. Could you see how you would find the measure for x? Take a look, where's x?
3x,
Right here. This is congruent to which segment?
18.
This one. Set them equal, solve for x. You have a number?
Yes.
Awesome. Soon as you find x, you want to find the perimeter of this triangle, which means you need to figure out what this is. Okay, you see how you would do that? All right, number 6 is very, very similar. All right, let's look at the last one. Number 7 is about a clock. Do we have a similar setup on number 7 as we did with 5 and 6? Yes. Do you think that you could find the measures of the different segments that you're being asked to find? If you can get through 5 and 6, you can get through number 7.
BE is equal to B.
Exactly. This BE is going to be congruent to this BD because we have two tangents coming toward a circle from the same common spot. Very nice. Let's look at 10.6 very quickly. We're doing really good on time. You guys are super awesome. Secants, tangents, and angle measures. So this is going to be using all of the stuff that we talked about today. Number 1 is going to be very similar to the very first part of your notes where you're looking at the measures of inscribed arcs. On number 1, are those secants intersecting inside or outside the circle?
Inside.
Inside, which means you're going to be using the inside formula.
Oh, cool. I need to do that.
Mm-hmm. Now take a look at this one. Where do those secants or lines intersect?
Inside.
Inside, outside, or on?
On.
On, which means this is an inscribed angle. So go back to 10.4 and look once again at your inscribed angles. That should help you figure this one out.
And
Okay?
number 3.
Number 3 is going to be the same way. Look at number 4 and 5. Two secants. And they're intersecting where? Inside or outside?
Outside.
Outside. So you're going to use the outside formula? Very nice. Flip the page, look at number 6. We've got the same sort of thing set up. Okay, but one of the lines is a tangent. It's okay. It'll be fine. Yeah, it's okay. Look at 7, 8, and 9. Same sort of deal? Same sort of thing?
Yeah.
Okay, sure. 8 and 9 are tangents, but you're going to have the same sort of thing happen. Okay? Number 10, same thing? Yes, but now we're in what a kickball word problem. But it's the same sort of idea as what we've already done. All right, any general questions on anything that we did today? All righty, thank you very much.